Well, in this video, we will discuss extreme values of functions of two variables. Many ideas will be directly borrowed from one-dimensional case, but of course, there will be complications, as one may expect. Well, to start with, the basic ideas, of course, don't change. That is, okay, let me say definitions. Okay, these are directly borrowed from one-dimensional case, so similar to an f from R to R. Okay, we say f from R2 into R, okay, has a maximum. Okay, this means by the very term, okay, absolute maximum, okay, value on a subset of R2. Actually, it should be in the domain, okay? So necessarily, of course, okay. If there is a value in S such that f of P0 or f of P is less than f of P0, okay, for every P in S. In other words, f of P0 is the maximum value. Okay. Well, this is what we call absolute maximum or just maximum. Obviously, we can make a similar definition for the minimum value, okay, namely and of course, you say absolute minimum and so on, if of course one has the opposite inequality. Okay. So it should read, a function of two variables has a minimum value on S if there is a value which is smaller than all other values on this set S. Okay. Now this value may or may not exist. So these values, okay, just as in one-dimensional case. Namely, okay, you can consider, for example, the usual paraboloid, okay, something like this. Okay. Then, of course, it has no absolute maximum, or just maximum, on R2, because it goes to infinity. Okay, but has minimum, which is 0 on R. Well, this is an example where you have an unbounded function. Well, in bounded cases, this can also happen. Or, for example, just consider the following example from one variable, generalized, of course. It's something like this. Suppose you have a surface, okay, which makes a hilltop at some point, and it has a ditch somewhere. And suppose that it extends, but it's bounded by these values. Now, obviously, this point is a maximum, this point is a minimum value. Now, let us change them a little bit. Take this point, okay, and instead of that, define the function here. Of course, all this rests on the XYZ coordinate axis. And take this point out and put it somewhere here. Okay. What happens now? Well, if these are the upper and lower values, if they were the biggest and the smallest values, by changing them this way, we just made this impossible. That is, there is no value which is biggest. It should be this one, but it's not a value because the value is here. Similarly, this should be the minimum value, but there's no value there. The value on top of this point is here. So this is not the smallest value. So this function has no maximum or minimum. Now this, of course, is similar to the case in one variable, okay, which very much looks like this. Okay. Well, this would be maximum value, make it 0. This should be minimum value, make it 0. So there are no maximum, minimum. Okay. By playing, you can do this. Of course, you observe that these are not continuous functions. Namely, here, by changing the value, we made it discontinuous. Similarly here. Okay. These are bounded, but not continuous functions. And we know that in the case of one variable, if a function is continuous on a closed interval, then it has a minimum and a maximum. Well, we have a similar theorem here. Okay. Let us recall the extreme value theorem. Okay. Namely, if f is continuous, well, f, of course, is R to R, is continuous on a B, then f has minimum and maximum values on it. Okay. So the extreme value theorem said that in one variable, if we have a closed interval, then f has minimum and maximum values if it's continuous there. Now, continuity is when, of course, limit and the value are equal. Well, the same situation happens for functions of two variables. Now, what is different, of course, is what's a closed interval? Well, in R2, like R, we do not have closed intervals. We have, however, sets which generalize closed intervals. We are, at this point, not in a position to characterize them rigorously, but unofficially, we will make the following definition. Okay, that means this is not a very mathematical definition because we are not defining everything we use, but we rely on our common sense. Okay. Well, a subset S in R2 is called closed if it contains its boundary. Okay. And okay, S in R2 is called bounded if there is a constant, now this part is rigorous, such that okay, the length of every P is bounded by M for every P in S. Okay, basically this says that S is contained in a disk, okay, with radius M. So S is contained in a disk of radius M. So geometrically, if you can put a set in a disk, okay, then it's called bounded. This is a nice rigorous definition, but closeness is not that clear because here we used the term that it contains its boundary, but we did not define what boundary means. However, our common sense in many practical nice cases says that we can fit it into our knowledge at this point. Well, examples, for example. Okay. Consider the first quadrant. Okay. Now, this set is closed because it contains its boundaries, but not bounded. Okay. Or, a simpler example, consider a disk of radius 1, but say you include all points on the circumference, but not these. However, you consider everything inside. Now, the boundary of the circle, the unit circle, is of course, of the unit disk, is the unit circle. But this doesn't contain it, so this is not closed. Okay. But it's bound because you can put it in a disk. Okay. So this is basically about closed and bounded sets. Of course, they don't go together all the time. But of course, if you close this part, namely, if you consider a circle with a side and a boundary, okay, then this is closed, of course, and bounded. Now, this closedness and boundedness is, of course, a new concept for us, but clearly it generalizes a closed interval, because a closed interval is obviously closed and bounded. Okay. The boundary of an interval can be regarded as the endpoints. It contains them, and it is a bounded interval, and therefore it's a closed and bounded set. So the extreme value theorem, or rather its generalization, for a function of two variables, which we will just state without proof, says that let B in R2 be closed and bounded. if f is continuous on D, then f has a maximum and a minimum value on D. We will resort to this in many cases. We will refer to it and use this theorem. Now, this only tells us that if we have a function of two variables, and if we have a nice domain, say a closed circle or a disk, then and if f is continuous, the theorem says it has a minimum and a maximum. Okay, the next question, how can we find them? Well, this is an entirely different story. Okay, finding minimum maximum values is a different story. Even in functions of one variable, if we just knew this much about the function, that it's continuous, okay, it was very difficult to find the maximum and minimum values. But if we knew that it had a derivative, well, then things were easy. Namely, okay, let us recall that for a function of one variable, okay, if f prime existed in AB, okay, then we could find minimum maximum values by doing the following. Okay, you recall this process, of course, namely by, okay, checking two things. This could happen at the endpoints or inside. So, by checking all critical points in AB, okay, well, this meant, of course, because there is a derivative, that if we have a minimum or maximum inside the interval, not the endpoints, then it should be a local minimum maximum. Okay. Since then, minimum maximum values are local minimum and local maximum, so f prime x0 would be 0 at such points. Okay. And we also checked endpoints. Namely, we looked at f of a, f of b, and f of x0. If x0 is a critical point, we took the biggest one, it was the absolute maximum, and the smallest absolute minimum. Okay, so this was the situation for a function of one variable. Now, in this case, we have some difficulties. Okay, what are they? Firstly, okay, what are local minimum and local maximum? That's one thing. Secondly, what's a critical point? Derivative must be 0 in one variable, but we don't have a derivative in two variables. So we have some trouble there. And finally, we also have trouble with the second part. Well, for a function of one variable, we just had two endpoints, a and b. So it was easy to check them. But here, the endpoint concept is replaced by the boundary. And on the boundary, we have infinitely many points. So it's clear that some things must change. We must generalize in this sense. Okay, let us first start with, well, what is a local minimum, local maximum for a function of one variable? Well, the definition is exactly the same, because that is the idea of a local minimum or a local maximum. So, definition, okay, similar to functions of one variable, okay, f of two variables has a local maximum, respectively local minimum, at p0, okay. Okay, I have to, I'm not starting to tell you how to find them at first, because we don't know about critical points, but just that, if, okay, there is a disk about P0, actually you need an open disk, okay, meaning boundary is not included. Well, this is still not a very formal way of saying it, but it explains things. Such that, okay, on this disk, okay, f of P0 is maximum, respectively. Okay. So what it says is that if you have a value which is biggest for nearby points, okay, it's called a local maximum, and so on. So if we sketch some hills and ditches, we can easily see what we mean by that. For example, it can happen that we have such a nice hilltop, but the surface does not finish there. The surface perhaps goes up. So this is such a surface. Well, clearly this level is not the highest point, because there are higher points here. But for nearby points, namely for points in here, on top of this small disk, this is the biggest value. So this is a local maximum, but not absolute maximum, because the absolute maximum maybe is infinity, and so on. Okay. Now, what is a critical point? Well, we defined a critical point to be a point where the derivative was 0, but the derivative was the slope of the tangent line. Well, what do we have to replace tangent lines? In the case of two variables, we have tangent planes. So a critical point for a function of two variables is where the tangent plane is horizontal, just like horizontalness in one variable. So, okay, a critical point of function of two variables is a point such that the tangent plane is horizontal. So here, it should be noted that because we define this geometrically by using the existence of the tangent plane, okay, we are assuming there is a tangent plane. Well, this is so exactly when f is differentiable again. Okay, so we assume f is differentiable. Now, what does the tangent plane is horizontal mean? Well, remember, okay, the tangent plane will be horizontal if a normal vector to it is k or minus k, which means that the first two components must be 0. But this is precisely when the partial derivatives vanish. That's to say, okay, and this happens when k or minus k is perpendicular to the tangent plane that is f sub x and f sub y at p0 are equal to 0. Equivalently, the gradient of f, of course, because f is a function of two variables, this is a vector in plane at p0, okay, is 0, 0. Okay, so this is the definition of a critical point for a differentiable function f. Now this says that, comparing it with one variable, that the derivative becomes 0 is replaced by the gradient being the 0 vector. So these are critical points. Now, an observation. Okay, if f is differentiable at p0, hence there are partial derivatives, okay, and there are directional derivatives, okay, and okay, f of p0 is a local maximum value. What happens now? Well, this is the biggest value for all nearby points. So, if we consider this picture, okay, at this point, at the top, we have the biggest value. So this is the surface. Okay. Now, let us take a straight line. Actually, some v parallel to it. What do we have at the top? Well, at the top, if we intersect this with this plane, obviously the intersection will be a curve of this form. Okay? Well, because this is the biggest value for all nearby points, on this curve, we indeed get a local maximum. So, okay, so on top of L, okay, f of p0 is still a local maximum. Well, from one variable calculus, we know that at such points, the derivative must be 0. So, the derivative, okay, on this vertical plane, okay, we are not in space anymore. We passed to a plane, and we have a curve in plane. This curve has a local maximum, and so its derivative must be 0 from our previous knowledge. But what is the derivative? There, it's clearly the directional derivative in the direction of v. So this is the slope of the tangent line, and it must vanish at this point. Okay. Okay, what does this mean? This means, of course, the following. Because f is differentiable, it means that gradient at p0 dot the unit vector here must be 0. Okay. Well, if we assume v is cosine alpha sine alpha, then f sub x at p0 cosine alpha plus f sub y at p0 sine alpha is 0 for every alpha. Because here L is not a particular L. It can be any line through p0. That means v can be any vector. So for any alpha, this will be 0. However, the coefficients are fixed. Okay. Now, if for every cosine alpha and sine alpha, this will be 0, it means that both of them must be 0, because you can simply take alpha, say, pi over 2. So this is 1. This part is 0. So this must be 0, etc. Okay. This implies f sub x at p0, f sub y at p0 must be 0. So p0 is critical. By the way, here you can take alpha pi over 2 and alpha 0. Okay. It says both are 0 directly. Similarly, for a local minimum, so we conclude the following. If f is differentiable, then any local minimum, local maximum point, okay, is a critical point. Okay, remember, it means that the gradient is 0 there. So this does not change for functions of two variables. Namely, local maximum, minimum, okay, implies being a critical point. So we can go backwards as we did in one variable. We can find all critical points and check if we have local minimum or a local maximum. Okay, this is, of course, possible. But of course, to determine that, we need some tests, as we did in one variable. Namely, we had a first derivative test. Remember, if the derivative is first positive and then negative, it was a local maximum. And in the other way around, it was a local minimum. But first, it's a critical point, and so on. Well, here, those tests are not that easy. Okay, because we don't have before x0 and after x0. P can approach P0 in infinitely many ways, so we have some difficulties there. But still, such points are among critical points. So this is one result, which is still correct for functions of several variables. At this point, let me emphasize that, as in the case of one variable, a critical point need not be a local maximum or local minimum point. Okay. We can see pictorially this directly. For example, consider something like this. Suppose we have the x cubed graph, but we shift it. So we obtain a three-dimensional version. Now, exactly at the point where we had 0 in two variables, in one variable, okay, consider any point here. Now, sketch the tangent plane. Okay, it would look like the following. Okay. And of course, it's horizontal. And because this is a z is x cubed curve, well, by the way, it is so. Just this. Okay. It's a polynomial, so it is differentiable. Everything is perfect. And because it's horizontal, gradient f at this P0 is 0, 0. So critical point. Of course, but it is not local maximum or minimum because there are higher values and lower values very near P0. However small you consider your points around P0, there will always be bigger and smaller values, just like y is equal to x cubed in two variables. But P0 is neither local maximum nor local minimum. Okay. But obviously this picture is borrowed from one-dimensional case. These are the properties of y equal to x cubed in plane. We just moved that graph parallel to the y-axis, and then we obtained such a surface. Okay. But in two variables, we have more complicated cases which cannot occur in one variable case. So, okay, a case, okay, particular to fx1, which cannot occur for a function R into R, is the following. Well, consider a curve like y equal to x squared. Obviously, you have a minimum here, and that's all. But think of this in two variables. So consider this. Okay. As you can imagine, it's a saddle. The thing you put on a horse if you want to mount a horse. So it's a saddle, but it has a very peculiar property. The property is that at this point, okay, when you consider the direction parallel to this line, then you get this curve. Okay. So in this direction, one has local minimum, as in the case of one variable. But there are other directions. For example, we could consider this direction, perpendicular to the original direction. And there, of course, we have a local maximum. So in this direction, okay, there is a local maximum. So depending on the direction in a saddle, you have a local minimum and a local maximum. This is the definition of a saddle point. Namely, if in some directions you have a local maximum, in some you have a local minimum, then you call it a saddle point. in some direction, you have local minimum. In some, you have local maximum. Now, this cannot happen for a function of one variable because you don't have many directions. You have just the x direction where x can move. Okay? That's all. Okay. Just before we continue, there are more complicated forms of this. Namely, you can talk about a saddle, okay? But at this point, somehow you have something like this as well. It means that you have two hilltops here. And of course, at this point, actually, the picture is bad, so let me make it correct. Looks like this. So this is a minimum in both directions. Okay? But it's a maximum, again, in the other directions. It's a saddle. But because of this split here, one hill, okay, splits into two hills. You can imagine that in geography, for instance. These are called monkey saddles. Okay, this humorous expression comes from the following. If you want to put a monkey on top of a horse, there will be a problem because it will have a tail. Okay, so where will the tail go? Well, if you have in the saddle two hills, the tail goes between them. So you have a monkey's saddle. Well, even more so, you can have more than two hills. So one hill may split into lots of hills, and you can have various valleys between them. So this is also possible. Surfaces are quite rich in this sense. So at any rate, we now know that a critical point need not be a local minimum or a local maximum.